Hello everyone, Mr. Choi here. So in this video, we will continue our study in motion. In the previous video, we have learned that motion can be measured by these three vectors: displacement, velocity, and acceleration. So in this video, we are going to learn on how to describe motion by different representation. So before we begin on the new portion, we will do a quick recap on the three parameters that were introduced in the previous video. So we have here displacement, which basically tells you the position with reference to the starting point. So this is a vector, meaning that it can take on both positive and negative values. And positive simply means that it could be forward, and then negative is just backwards. Then we have velocity, which is the counterpart for speed. So this is the vector version of speed. What do I mean by vector version? So speed is a scalar, meaning that it can only take on positive value. It can only have a magnitude. But for velocity, it can have positive 10 meter per second, or it can have negative 4 meter per second. And the plus and minus sign basically tells you the direction of motion. So a negative 4 meter per second means that it moves backwards 4 meter every seconds. Okay, so the plus and minus just is just an indication of the direction. Okay, when we want to find out which one is moving faster, we look at the numeric magnitude. And lastly, we have this parameter acceleration. In a nutshell, it tells you whether the object is speeding up or slowing down. In most cases, whereby the velocity is positive, we say that a positive acceleration is speeding up and a negative acceleration is slowing down. That is in the case whereby velocity is positive, which most of the time is the case lah. But there are some cases whereby the context is set to test whether you have this awareness. They may adopt a sign convention whereby the object is moving in the negative direction, meaning that the velocity is negative. Then in this case, a positive acceleration is slowing down and a negative acceleration is speeding up. Okay, but most of the time, velocity is actually positive. Yeah. So that is what we have covered in the previous lesson. Today, what we are going to do is that we are going to learn how to describe a situation, meaning that we are going to learn how to describe motion and represent it by two different formats. The first format is that we describe and represent it in terms of a graph. There are two graphs that you need to learn. One is called velocity time graph. The other one is displacement time graph. So displacement, the algebra that we use to denote displacement is actually S. Okay. Then after that, we will also learn how to describe in words, how to describe motion in terms of velocity and acceleration. So things like, it is moving at constant velocity, increasing velocity. What does decreasing acceleration means? Does it mean that it is slowing down? Things like that. Okay, so that's what we are going to cover today. And you should have finished this part. If you have question on this, meaning that after you check your answer in SLS and you still do not understand why, you can drop me a WhatsApp. Okay, this part you can get the answer from the textbook. So what we are going to do is that we are going to do a quick, we are going to focus on this part on how you can interpret the graphs, velocity time graph and displacement time graph. So before we begin, let's start off with something that is very simple. For example, speed. So in lower secondary, you have learned about speed. So to calculate speed, it is quite straightforward. Let's say I have a man here at the start point, and the start point is denoted at 0 meter, and it moves to the right, positive direction, and it takes 6 seconds to reach 4 meter. So how do I find the speed? So in your lower set, actually to find the speed, what you are doing is that you take 4 meter divided by 6, right? So in essence, what you are doing is that you are calculating the change in distance and then you divide by change in time, right? That's how you get 4 on top, because this is how you get 4 minus 0, right? That's how you get 4, right? How do you get the time? Or you took 6 seconds and you minus 0, right? That's how you get 6. So if we turn this understanding into a formula, it will look like that, right? You take the final distance minus the initial distance. That is what you did over here, right? Then after that, how do you find the time taken? You take the time reached when you hit D2, and then you subtract it from the starting time. That's how you get 6 minus 0, right? So if you look at this formula, you will notice that this looks like the gradient formula where you have y2 minus y1 over x2 over x1. So meaning that if now we are to describe this very simple motion, a man moving to the right by 4 meters in 6 seconds, in a graph, if we want to represent in a graph and we want to represent this in terms of a distant time graph, we will have something like this. So when we have this, you can see that actually the coordinate over here, if you read it, will be x coordinate followed by y coordinate, right? So that's how you get t2, d2. So same thing for here. So if you look at this graph, you will notice that this expression and this one actually looks very, very similar. So actually what we can tell from this very simple illustration is that you can say that the gradient of a dt graph is actually the speed of the object. That the gradient of a dt graph can tell you the speed of an object, right? So if we extend this understanding to vectors, so instead of measuring speed, now I want to measure velocity. So because velocity is a vector, distance now will have to be changed to displacement. So if I do the same thing, you will see that S, by the way, remember this S here is representing displacement. So if we want to calculate velocity, it is still the same thing, change in displacement over change in time, right? You will see that if now I have a displacement time graph, the gradient of this displacement time graph, if I were to calculate the gradient of this displacement time graph, I will arrive at the same expression as my velocity formula. So we can actually extend this and say that now we realize that this gradient of a displacement time graph will tell me the velocity, right? So in a way, if now I have a graph of displacement time graph, how can I obtain the velocity of an object? Or to find the velocity of an object, I just need to take the gradient of the displacement time graph. So this is the first new content that we learned, that in a distant time graph, the gradient will give me the speed, because this is distant time graph. And if I were to have a displacement time graph, how do I get the velocity? Well, I just need to calculate the gradient at the point of interest, and the gradient will tell me the velocity of the object, right? So that is content number one. Now, how about if now if the question didn't give you the displacement time graph, but instead it gives you the velocity time graph. Now, velocity time graph is a bit tricky, okay? But let's look at what we have learned in the previous lesson, the acceleration formula. So in the acceleration formula, we have a equals to v minus u over t, right? And now we know that v is the final velocity, u is the initial velocity, and t is time taken. So in essence, when we do this, we are doing something like that, right? Final velocity is v2. The time at where I reach v2 is t2, right? So if I generalize it, I will be able to see that my acceleration formula actually takes on this form as well. And by the same logic, if now I describe my motion and I represent it in terms of a velocity time graph, I can have something like that. And you can see that the gradient expression of a velocity time graph and the expression for acceleration over here, they are actually the same. So we can generalize this and say that the gradient of a velocity time graph will actually give us the acceleration of an object. So this is the second content knowledge that we learn, that in a speed time graph or a velocity time graph, the gradient will give us the acceleration. Okay. Now, how about other things? Can I obtain other things from a velocity time graph? Right? Well, let me challenge you to think a little bit further. What if now I have an object that is moving at speed that is rising? How can I obtain the distance traveled by this object? So for example, let's say my object at time equals to 0 is at rest, at time equals to 1 it is moving at velocity of 4, at time equals to 2 my speed actually rises to 8, and then at time equals to 3 the speed actually rises to 12. Now in lower set, what you learn is that distance is actually equals to speed times time, right? However, in this case, the speed of the object is not constant. So what are you going to sub into here? Are you going to sub as 0, 4, 8, or 12? How do you do it? So that poses a challenge to us, right? Because now motion is not limited to constant speed. The speed actually changes. So how are you going to get distance? Now to do this, we need to actually sketch a VT graph. Now when we sketch a VT graph, you can see that 0, 0 over here, right, comes to this point. This is 0, 0. Time equals to 1, v equals to 4. So time equals to 1, v equals to 4. Time equals to 2, v equals to 8. Time equals to 3, v equals to 12, right? Then we will have a graph like that. So how do I find the distance? Now what we are going to do is that we are going to use estimation. So now let's do an estimation. Let's say I'm doing this estimation, right? I estimate that between time 0 to 1, my speed is going to be constant at 4. So meaning that from speed 0 to time, time equals to 0 and time equals to 1, I assume that my speed is constant at 4. Then when the object transit to t equals to 2, I assume that the speed is constant between 1 and 2. So it goes like that. Right. Then after that, when the time reaches 3, I assume that my speed is like this. So what I have here is that I have estimation of another VT graph like that. Right. So now if I look at this black line and the original one, which is the actual motion, is it a good estimation? Well, there's still some variation, right? How can we make a better estimation? Well, what I can do is that I can make the step more refined. So maybe I don't assume that the speed from 0 to 1 is always 4. Let's assume maybe the speed is 4 when time is 0.5 to 1. And I assume that from 0 to 0.5, my speed is 2, right? And I do it the same way, right? Maybe I assume like from here to 1.5, my speed is 8. But then 1 to 1.5, speed is 6, right? And then I do the same thing for here. So now if I look at this pink color estimation versus the yellow one, pink and yellow, which one is a better estimation to this green original one? Well, you can see that actually the pink one is a closer estimation, right? How about if I do it in such a, then you may be thinking at this point, teacher, okay, so now I understand if the step is smaller, then obviously it is a closer estimation to the green line, right? But how does this solve my question? How do I find the distance? Well, remember what we have done at the beginning. We say that, oh, actually distance can be equals to speed times time, right? Provided that my speed here is constant, correct or not? So in estimation 1, how can I find the speed? Well, how can I find the distance? So in estimation 1, what I can do is, I assume that speed is 4, right? And the time taken is 1 second, correct or not? So I can take 4 times 1, right? to find the distance traveled in this estimation, right? 4 times 1 give you what? 4 times 1, isn't it the area under here? Right, then after that, what do I do? Oh, okay, in the second, then I estimate 8 times 2. So I will take this, right? 8 times 2. Then if I want to find the distance traveled in this 3 seconds, my estimation one basically will give me this whole chunk lah, right? The distance traveled here plus the distance traveled here plus the distance traveled here will give me an estimation correct or not? Then how about if I do this? Well, if I do this, then my estimation will be more refined lah, because now I break my speed into 0.5 second steps, correct or not? But you can see that actually estimation 2 will be a more accurate estimation than estimation 1, right? Because you can look at my motion line, the yellow highlighted one versus the pink one. The pink one is a better approximation of the green color one, right? So if I extend this logic and I say that, oh, okay, I don't want to do a 0.5 interval. I don't want to do this 0.5 interval thing, right? At first, this one is 1 second interval, right? Then I make a more refined estimation and I say this is my 0.5 second interval, right? What if I make it into like 0.0000001 interval? Then it will look something like that, right? It will be a very, very refined step, right? And once I have this very, very refined step, as long as I find this very small change in time, right, multiply by this height, I will be able to, and then if I sum all this up, it will give me the distance, the estimation of the distance travel when my speed is changing, right? But if you look at this, right, if I go and find every column by the small change in time multiplied by the speed, small change in time and then the speed, what do you notice? This black color thing here that I am filling up as strips of rectangles, right? If I do this, isn't it the same as I just find the area under this graph? If I find this area under this graph, isn't this what I'm doing here? Instead of finding very small area of the strip of rectangle here, I can actually just find the area under the VT graph, right? So actually what we can do is that we can estimate and say that actually to find the distance of an object that is moving at changing speed, I can actually find the distance traveled simply by, let's say if I have this motion and I'm interested to find how much displacement has the object traveled between, let's say time equals to t3 and time equals to t4. I want to find how much distance it has covered for this particular object. Well, to find this, I just need to find this area. So this area is called the area under the VT graph, right? And because velocity time graph give you a vector measurement, this thing that you are finding, the area, right, is actually the displacement. Meaning what? Meaning that I can actually have negative displacement, right? So if let's say I want to go and find time t4 to t5, well, t4 to t5, the area so-called under the graph is this area. So it's not this area, okay? This is not called under the graph. When we say under the graph, it is actually the area between the VT line and the x-axis, right? So this is negative displacement. This is positive displacement, right? So what we have learned is that there are two things that you can find from a VT graph. First one is that the gradient of a VT graph will give you the acceleration. Second one is that the area under the VT graph will actually give you the displacement. Okay, and this area under the graph actually refers to the enclosed area between the VT line and your x-axis, which is your time axis. Okay, so what we have learned today in this video is that in motion, okay, we can of course measure by these three parameters, but we can also describe motion using this graph, VT graph and displacement time graph. And from this graph, we can obtain several information, right? In VT graph, we know that the gradient will actually give you the acceleration, and we learn that the area under the graph will actually give you the displacement, right? And then for the displacement time graph, we know that the gradient will actually give you the velocity, right? So this is what this video has covered. Okay, hope you enjoy it and you understand what I mean. After that, you can watch video 2, okay, and then we will do some practices using this worksheet as well. Okay, see you in the next video.